So in this session, we discuss about the mathematical characterization of the cake filtration process. Now we'll consider the special case of constant pressure filtration. Before starting the mathematical derivation, you need to keep in mind two important things. There will be several steps involved in the mathematical characterization. Sometimes this may raise questions, why are we doing this? This is done based on two main principles. Number one, we want to express some variables or parameters which are hard to measure based on other variables which are easier to measure. So that's number one. Number two, we will always want to express the mathematical equation in a simple form that's easy to express as a plot, meaning that the mathematical formulation should be simple enough that you can easily plot the variables against each other. So for this mathematical derivation as well, we'll follow those two principles. Now to start with, let's look at a schematic representation of the filtration process itself. We'll just simply draw the medium and the cake in order to derive the necessary mathematical equations. So this is what we will take as the filter medium. As you know, for cake filtration, there is a thicker layer of cake. So if we take this layer to be that of the cake, so this filter medium and the cake together forms the main system that we'll use to derive the mathematical formulation. So in a 3D formulation, the filter medium will be something this, and the cake will be something this one. Now to keep it simple, we simply look at the two-dimensional representation. We'll concentrate our focus here within this region. So just to give you some notation, if you consider the pressure here, it's PA, and pressure here is PB, meaning the total pressure drop where the material is flowing from this direction, the pressure drop will be PA minus PB. In the boundary of the cake and the medium, the pressure is represented as P prime. We take the thickness of this to be Lm and this thickness of this cake to be Lc. Now we'll take a small segment of this cake to start our mathematical derivation. So now if we do this, consider a small segment of the cake whose thickness we'll take as dl, and we'll represent the distance from the filter medium interface to that portion to be L. So those are the main notations used here. Now to start characterizing the process, we'll start with the pressure drop here. So this overall delta P is represented by PA minus PB, and also it can be represented by pressure drop within the cake plus pressure drop in the medium. So this delta PA minus delta PB, this PA minus PB, if I write it as PA minus P prime plus P prime minus PB, give you delta P the cake plus delta P in the filter medium. So that's just keep in mind the delta P formulation for the overall process. Now we'll start the mathematical derivation by using an equation that characterizes flow of liquid through a porous medium. Now consider the cake to be a porous medium and the liquid going through that particular porous medium. For this case, we know a famous equation, what is called this Kozeny-Kármán equation, that we'll be using. Now do remember that this Kozenik-Harman equation expresses the pressure drop of a fluid passing through a porous medium for laminar flow. Now for cake filtration, why we are considering laminar flow? The solid particles in cake filtration are very small, and for those small particles, considering a laminar flow is justified. Now let's look at what this Kozenik-Harman equation says. So this equation represents the pressure drop per unit length, and this is given by a constant term 150 mu u over ys dp squared 1 minus epsilon squared over epsilon cube. Here in this equation, this is the sphericity of the particles. This is the diameter of the particles. Epsilon is the void fraction. Mu is the viscosity. So viscosity of the liquid, and this u is called the linear velocity of the fluid. So keep in mind all of these terminologies. Now to start with, we'll try doing some sort of replacement in this equation. First one will be to replace this dl term by some mass of particles. Now to do that, we'll represent this dp with all these terms remains there. Now look at this length dl. So within this length dl, there is the solid and there is the liquid. Now that particular dl, if you look at in this 3-dimension, for this particular part, if you take the area, this face area of the filter medium to be A, we can write, so we'll have this dl term here. So we can write volume of this layer. So you can now consider, again, go back to the 3D formulation. We need to find out what is the volume of this layer. So it has a thickness of dl and a face area of A. So dl times this area to be A. So the volume will be A dl. So we have volume of the layer A dl. Now if we have this void fraction to be epsilon, then we have void volume in the layer will be A dl epsilon. So then what is the volume of solid? Again in the layer will be A dl 1 minus epsilon. With epsilon fraction is the void, so 1 minus epsilon is the solid. So what is the mass of solid? In the layer will be rho p A dl 1 minus epsilon, but simply rho p is the density of the particles. So you multiply the volume by density, you get the mass. So if you represent this to be by dm, remember that the small amount of mass. So this is the mass representing the mass of solid in the differential layer that we are considering. So from here we get dl will be dm over rho p A 1 minus epsilon. Now if I replace this dl by this term here, we'll end up getting dm over rho p A 1 minus epsilon. So now this 1 minus epsilon and this 1 minus epsilon is squared. One of these cancels with this one. So we can get rid of this square and this term here. So we'll be getting, so just simply replace the dl by the dm term to get the equation in terms of mass. Now we'll try to integrate this. So integrate over this, and all of this you see here 150 mu So all of these are constant. So we'll integrate over dm. Now consider what the limit for the integration. Now at the beginning, the cake start forming on the interface and start going on. Initially the pressure would be P prime to a pressure P A. At the beginning, there was no mass accumulated, so that's 0. And if you consider at some time, the mass is accumulated, the mass of the cake, so mc. So we have this limit P prime and Pa, and here the corresponding limits for dm is 0 to mc. Now if we do the integration, you will have on this side Pa minus P prime, which we have denoted by delta Pc, so which is the pressure drop in the cake. We'll have all of these terms here. And it will get mc. So this is one of the relation that we can get by doing the integration. And from here, we see we'll formulate a new term. So if we just simply do a little bit of rearrangement of these terms, we'll get delta Pc over mu u mc over a equals 150 over pi s dp squared 1 minus epsilon over epsilon cube, and we'll have another term here rho p. So now look at here, we have taken all the constant solid properties on the right side. Remember what is the purpose of this formulation? That on the right hand side, these are all the constant terms for the solid particles. So sphericity is constant, diameter is constant, void fraction is constant, and also density is constant. So all the constant term for the solid particles. On the left hand side, we have this viscosity for the fluid, the linear velocity, mass of solid in the cake, and then the area, and this delta Pc. So these are all solid properties which are constants. This constant is defined what is called this specific cake resistance. So we have this specific cake resistance given by alpha equals delta Pc mu u mc over a. The definition of this specific cake resistance is given as follows. If in this equation you see that if mu, u and mc over a all are 1, then alpha becomes delta Pc, meaning the pressure drop in the cake. So specific cake resistance is defined as the pressure drop that will happen in the cake if mu, u and mc over a all equal to 1. Okay, so mu is 1, u is 1, and mc over a it's 1 as well. Now this is called this specific cake resistance because it's per unit of mass per unit area. So the resistance per unit of solid in the cake per unit area. So we have this definition of specific cake resistance here. In some way, this is one of the characterization of the cake part. Now what about the filter medium part then? Now similar to this specific cake resistance, we define one term what is called this filter medium resistance. Now filter medium does not involve any sort of mass of solid in it, so this term will not be there, but it will be dependent on the liquid viscosity, liquid velocity. Filter medium resistance defined as Rm equal delta P in the medium over mu u. Similar to the specific cake resistance, however, this mc over a part is not there simply because in the filter medium there is no solid accumulation. So these are the two basic definitions, filter medium resistance and the specific cake resistance, that we'll be using in the next phase of this derivation. Now we have these two definitions, specific cake resistance and the filter medium resistance. Do remember the idea of defining this specific cake resistance, that it was a constant. It depends on the solid properties. So if you can determine for a particular solid, for a particular filtration process, you can get the value of alpha, then you can use it for other operating conditions as well. So now go back to the definition that we had for delta P. So delta P is equal to delta PC and delta PM. So you can write delta P and you can write delta PC in terms of this. So it will be alpha mu u mc over A, and for delta Pm it will be Rm mu u. Now if we define two terms, is V, what is the volume of filtrate at any time, and we define C as the mass of solid particles per unit mass of liquid. So if you have C is the mass of solid particles per unit mass of liquid, and you get at certain time V to be the volume of the filtrate. So how much solid will be collected as a cake, that can be given by MC equals V times C. So if you use this equation to replace MC over here, we'll get delta P to be, MC will be VC. We'll have this mu u term for both. So mu u alpha MC will be VC over A plus Rm. The linear velocity of the fluid can be obtained in terms of the volume of filtrate as U equals the volumetric flow rate over the area, that give you the velocity. So you see here the face area of the filter medium is A, flow in this direction, and the area perpendicular to the flow is given by A. So when you divide this volumetric flow rate, which is dV over dt, divided by the area perpendicular to the flow, you get the velocity. So here you get delta P becomes mu dV over dt 1 over A alpha VC A plus Rm. So now we'll do a simple mathematical manipulation here to take this term dt on the other side. We'll have dt to be, we'll have dt is taken on the other side, mu alpha C over A squared, and delta P comes here, times V plus, and dV remains here, plus you have mu Rm over A dV. So just taken this dt term on the left side, all other terms remains there, and we took the delta P term, should be here, delta P term on the right hand side. Now we have done it just to do the integration. Now we integrate this term now for time 0 to t, and for that time at t, if the volume of the filtrate is V, we can integrate this equation. So if you do this, we'll have the limit of integration between 0 time t. At time 0 there is no volume collected, so that's also 0, and we can have this limit to be V and 0 and V. And if we do this integration, in the left hand side we will have t equals mu alpha C A squared delta P V squared over 2 plus mu Rm over A delta P V. Now this is the equation of the t as a function of V square and V. A little bit modification will give the equation in a more convenient form. So if I divide both sides by V, we will have t over V equals mu alpha C Now, what is the benefit of expressing it this way? Now, you can see that this equation, if you take t over v is one variable, v is another variable, and this is your y, this is your x, you see that y is a linear function of x. So, in a textbook, it will be written as something as t over v equals some kc over 2v plus 1 over q naught. So, q naught is really given as the initial flow rate of the filtrate. So in this equation, you see that if you plot t over v, function of v, you will get a straight line. Where the slope of this straight line is given by kc over 2, and this intersection is given as 1 over q naught. So now if you go back to these two principles that we discussed at the beginning, the number 2 is the final expression is obtained in the form of a straight line. That's the simplest possible relation that we can get. Other thing is that now if you can measure the volume of filtrate, which is easy to measure, you can relate it to all these parameters kc and q naught. Now kc here is simply nothing but mu alpha c over a square delta p, and 1 over q naught is simply mu rm over a delta p. You see that by simply measuring the filtrate volume as a function of time, you can get a straight line. From here you can get the value of kc and q naught. And when you get the value of kc, you see that if you know what is the viscosity of the fluid, what was the solid content, what is the filtered area, and if you can measure the pressure drop, you can get the specific cake resistance. So similarly, you can get from the intercept, you will get this term, and in this term, if you know the viscosity of the liquid, area of the filter medium, filter area, and you measure the pressure drop, you can get the filter medium resistance. Again, going back to the definitions of the specific cake resistance and filter medium resistance, you look at those are expressed in terms of pressure drop, and if you can measure the pressure drop, you can get those parameters as well. Do remember that for this case, you need to measure the pressure drop not in the interface, but the pressure drop in the entire filtration process, meaning that drop in the cake plus the pressure drop in the medium. And using that, you can get the measure of this specific cake resistance and the filter medium resistance. And from one set of experiment, you can find out the value of alpha and Rm. You can use that to estimate, for example, what will be the time required to get certain amount of filtrate if you increase the area or if you increase the pressure drop. Remember that for this case, this is constant pressure filtration process, meaning the volume of the filtrate will vary. However, the pressure drop is to be maintained constant.